Okay, this is a presentation of the my project for EC 595 simulation of the self-balancing robot using ROS. The overview of the project. The goal was to simulate the dynamics and control of the self-balancing robot using robot operating system and Gazebo. This is done by state space control as described in the mathematical model and control strategy of a two-wheeled self-balancing robot paper that Micho provided. Gazebo model of the robot was built using Unified Robot Description Format, URDF. CAD model of the robot and photos were obtained online through that website. They were imported into SolidWorks and converted to .stl mesh. Controller node was developed in ROS. Here's the robot model on the left in SolidWorks, and then on the right in Gazebo you can see the green section of the robot. Actually, there's an upper body which includes the top two plates, the threaded rod, battery, breadboard. I removed the Arduino to reduce the number of complex surfaces and the file size. Then there's a lower body which consists of this plate, some mounting brackets and nuts and bolts, and two motors. And then the wheels on either side are separate from the robot body. There's a wheel and a hub on each side. And that's pretty much it for the robot model. Mass properties were included in the simulation. ROS concepts, pretty simple ones: publisher and subscriber, eigenmatrix, pointers, symbolic equations to solve the state space equations, effort controllers to command the torque to each wheel, and Gazebo model states was used to extract angular velocity, the pitch angle, as well as linear velocity of the robot. Instead of using simulated sensors, this allowed for us to get perfect signals from Gazebo. Controls overview. Utilize state space control, as you can see in this box here, dashed box. There's two PI controllers in series with that state space control. They're parallel to each other, but then in series. The linear velocity set speed, and then differential velocity to allow for the robot to turn. They go through the PI control, so you set your desired speeds there, and then get summed with the feedback from the state space control here. And you can see in the state space control you have your robot here. Inputs are torque commands to the left and right wheels, or actually in this case voltage, and then the output's torque. Current was not used in the state space control. Phi, which is the pitch angle, omega is pitch angular velocity, V is the linear velocity in the x direction of the robot, and then differential velocity was not used in this project. Phi, omega, and V are fed back and multiplied by feedback coefficients or gains, and then go back into to be summed as feedback with the two PI controllers. So that's pretty much it for the controls. State space equations. The A matrix basically is the partial differential of the equations at the bottom of the screen with respect to the X matrix, which X matrix in this case is phi, omega, and V. And then B matrix is a partial differential of these equations with respect to U, and the U matrix is equal to commanded torque ND. You can see the equations here: d phi dt is equal to omega, d omega dt, and dv dt are pretty long equations. The equations were linearized and discretized to obtain an estimate of the current position. Estimate of current positions fed back and multiplied by feedback coefficients to determine voltage and then current. The gains for the feedback coefficients were tuned through trial and error, but better tuning could be achieved by utilizing procedures mentioned in the paper. Motor torque is then calculated by multiplying the torque coefficient, or multiplying current by the torque coefficient of the motor, and then that torque is then converted to, or is then published to the effort controllers to command torque to the wheels. U here is actually voltage, and solve this equation here, plug in the numbers here, so wheel radius minus k phi times phi plus k omega times omega plus kv times v. Ignore ki times I. I is equal to 1 over the resistance times voltage minus the torque coefficient times linear velocity divided by r, your wheel radius, minus omega. And then once you obtain the current, you plug that into this equation over here, multiply it by your torque coefficient to get your torque, your desired torque at each wheel. The video of the robot simulation loads up here. The robot initially set up to tilt forward at 0.2 radians. Otherwise, it would be perfectly balanced, and there wouldn't be a need for the controller. You can see the collision geometry for the upper body, the lower body, and then each wheel has a cylinder on it as well for collision. The robot's balancing pretty well. You can see that there is a linear velocity in the forward direction. I believe if I implemented the PI control, I would be able to get the robot to remain stationary, and that is planned to do in the future. Just don't have time for it at the moment, so that is future work. And that's pretty much it. The robot balances pretty well. Control works well. So that's it for the video. Summary of the project. Self-balancing robot was successfully simulated in Gazebo. State space control balances the robot well. PI control of robot linear velocity is to be implemented in the future, and hopefully differential velocity as well. Tuning of the robot could be improved using Ackerman's formula or LQR. Other potential future work includes adding LiDAR or a camera for simulation only, maybe develop some cost maps, and also to physically build the robot. Challenges included implementing state space control and extracting the model states from Gazebo messages. That helped me up a little bit at the end. I guess that's the project. Learned a lot in this project and throughout the class, and look forward to using ROS more in the future. One more slide, just references the website that was the inspiration for the project and where I got the CAD files from, and also the paper that was referred to throughout the presentation and used for all the equations in my project. And I guess that's it for the project. Thanks again.